All right, here we go with our fourth practice from 2015. This very likely to show up. It's a combination problem with a differential equation that you see here, dy dx is x times the quantity y minus 1 over 4, but it also includes a slope field. Slope fields, you should really hope that they show up because it's a little bit tedious, but it's very easy. The 8th grader could do this. So what they're asking us to do is, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. So there are 3 points here, 3 points at all 4. If they ever give you one of these and there's a variable in the denominator, for example, let's say they had an x in the denominator, the slope would be undefined at x equals 0. So they would generally don't ask you to fill in those slope fields if the slope is vertical there. Anyway, this one is not that way. And we have these points down here, and it seems like it's going to be a lot of work to go compute the slope at 12 different points. However, this slope, this rational function, rational expression, will be equal to 0 if we think about kind of some interesting places. This would be equal to 0 when the numerator is equal to 0, which would happen, of course, when x is 0 or when y equals 1. Think about putting a 1 in here. That's going to make that numerator be 0, which is going to make your slope be 0. So at any points where we have an x value of 0 or we have a y value of 1, we're going to have a 0 slope. So I'm going to draw these slopes in red so they pop off the page a little bit. So the places where x is 0 is along the y-axis. So we're going to have a 0 slope here, 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 and here. And also at the places where y equals 1. So if y equals 1, our y value is 1 right here and right here. So we knocked out 6 of the 12 very easily. So let's go and work at these places where x is negative 1, this point, and this one. So if x is negative 1, let's do it when y is 2. We'll start, or I'm sorry, when y is 3 up here at the top. If y is 3, then our slope would be negative 1, 3 minus 1 over 4, which is negative 1 times 2, which is negative 2 over 4, which is a slope of negative 1/2. All right? So we need to demonstrate a slope of negative 1/2, which of course means we'd be going down 1 and over 2. So what we can do is kind of, starting at this point, kind of aim toward that point over there, which would be a slope of negative 1/2 away from it. So I'm going to kind of draw that slope in there, and we're good to go. Let's do the same thing at negative 1, 2. And now we're going to have a slope of negative 1, 2 minus 1 over 4. I think you can see that's going to be negative 1 times 1 over 4, which is negative 1/4. So now our slope is just negative 1/4, which is a very shallow slope. Kind of hard to draw, but I'm just going to try to make it look a little less steep than the one before it. And now down at the bottom here for this point, our coordinates are negative 1, 0. So we can put negative 1, 0. And we are going to get negative 1 times 0 minus 1 over 4. And that is going to give us a positive 1 over 4. So now we're going to have a slope of positive 1/4. So very gently increasing spot right there. Come over here, we can do the right side. We can hit this one when it's 1, 3, 1, 2, and 1, 0. So let's hit 1, 3. We would get 1, 3 minus 1 over, let's see, our y value would be, I'm sorry, our denominator is 4. That is going to get us, let's see, 1 times 2 over 4, that's 2/4, which is 1/2. So put a 1/2 in there. At that was for this point up here, so I guess I should draw that in there. Let's get ourselves a red pen and put that in there at a slope of 1/2. So kind of mirroring what we saw on the other side of the y-axis. Now at 1, 2, I'm in red. I'm just going to stay in red. 1, 2 minus 1 over 4. That's going to be 1 times 1 over 4, which is 1/4. And you're seeing, again, kind of mirroring what was happening on the left side of the y-axis. So predicting with this slope down here at negative 1, 0 with a slope of 1/4, I'm going to predict that at positive 1 comma 0, we're going to get a slope of negative 1/4. And we'll see if that's true. 1 times 0 minus 1 over 4, and sure enough, that does it. So here we have a slope of negative 1/4, so just slightly negative. And there you go. So just, that's it. We probably only earned 2 points out of the 9 for that. But I do want to let you know, they might ask you to sketch the solution at a particular point, like down here when we get to part B, which we may as well start right now. When they give us the fact that there's a solution to this differential equation that has the characteristic that f of 1 equals 3, which would be this point here, what you would do is just kind of, put the point there and then follow the slope field lines to kind of determine where your curve's going to go. So it would look something like that. It's probably some kind of hyperbola or something like that. Anyway, let's move on to part B now and see what we have here. F is the solution with f of 1 equaling 3, so we have a point. I don't know why I put that in parentheses. We got a point, 1 comma 3. And they want us to write the equation of the tangent line at 1, 3. So we have the point, we need the slope. Well, we already did that. They'll do that a lot on these free responses. You can go back and use information. At 1, 3, we know our slope is a half, so we can go ahead and fill that in, and then write the equation of the tangent line using point-slope form. So y minus 3 equals 1/2 x minus 1. Bring the 3 over to the other side. 1/2 of x minus 1 plus 3. So they would certainly accept this as the equation of a tangent line, but you notice here at the end they ask us to use the equation of a tangent line to approximate f of 1.4. So all that means is you're going to plug 1.4 in for the x value, and I'll do that in blue. And so we're going to have y equals, we should say f of 1.4 is approximated by y evaluated at 1.4, which is 1/2 of 1.4 minus 1 plus 3, which is 1/2 of 0.4 plus 3, which is going to be 0.2 plus 3, which is 3.2. So there's our approximation of, so we could say f of 1.4 is approximately 3.2. Now, back to what I was saying with that whole idea of sketching a solution. They do ask that. So what you need to do there is do something like this. You would highlight the point, and sometimes they will do that. They'll make it extra big or something like that. And then you just kind of follow these slope lines that are giving you a guideline for how the curve goes, just so you meet them. And your curve would look something like that. And that's the sketch of the particular solution at 1, 3. Now, what we did here with this tangent line that we did in red, I'm going to actually say look at this equation here, this guy, is we came up with the equation for the tangent line at that point, which would look something like this. And this 3.2 value that we approximated is just this. There's a point over here somewhere that would have the coordinates 1.4 comma 3.2. I lied, that's really not. There's a point here that's 1.4 comma 3.2. And that's this point. And what we're doing is saying, oh, that point on the blue curve, the actual function, has 1.4 comma something. And we're saying because our tangent line is pretty close to our curve at that point, 3.2 is a pretty good approximation for that y value there. And they could ask you, is it an overestimate or underestimate? And you'd say, well, because the curve is concave up at that point, it's an underestimate. Those are the kind of follow-up questions they can ask. Okay, this is where the heart of this problem lies. Part C is where we're asked to find the particular solution. We're asked to find the equation of that blue kind of sketch that I put on the last page. So we've got the point 1, 3. And the very first thing we got to do here is, the goal is we're looking for, y equals. Okay, we're looking for an equation, y equals blah, 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 where we have everything accounted for based on this necessarily being the derivative of y with respect to x, and it being such that our initial condition is satisfied as well. So the very, very, very first step with this is you take a look at your formula for your slope, and you have to mastermind what you would need to do algebraically to get your y's with your y's and your x's with your, y's with your dy's and your x's with your dx's. And I think you could see if you're necessarily going to bring the dx over here, but you're going to need to take that y minus 1 and bring it down here. So hopefully everybody's familiar with cross multiplying or whatever. But essentially, our first step is to separate those variables. Get your y's with your dy's. So that's going to be dy over the quantity y minus 1 is going to be equal to x over 4 dx. And that is critical. This question might be worth 5 points. And generally the rubric will say something like, you get 0 points. I don't care how much good calculus you do in here or understanding. You get 0 out of the 5 if you don't separate those variables first. Because it's meaningless at this stage in our mathematical career to have y dx or something like that. You can't have this variable be different than the variable with respect that you're integrating to. So that is like a nonsensical statement. And if you do something like that, you've demonstrated a lack of understanding, and they're going to say you get no points. Having said that, the next step now is we integrate both sides. So you better remember that the integral of 1 over x dx is the ln of the absolute value of x plus c. If this quantity down here, as long as its derivative is 1, so for example 1 over x plus 17, the derivative of x plus 17 is still 1. So that is just going to be the ln of x plus 17, absolute value plus c. It's really good to know that because it's going to come up somewhere in the test. So the fact that this guy has a denominator of y minus 1, it's going to integrate to the ln of the absolute value of y minus 1. We're not going to put a plus c on this side because we're going to put a plus c on the other side. You might think of this as being the integral of 1/4 x dx. X over 4 is the same as 1/4 of that. So we're going to increase the power to x squared, and we're going to divide by 2, which is going to make this thing 1/8 x squared plus c. Now, this is usually the best time to go ahead and use your initial condition that x is 1 when y is 3, or y is 3 when x is 1, to solve for c. So this is going to be a little sticky. Sometimes they rig this so that you get a nice number over here, but we're not going to get the nicest of numbers. We're going to say the ln of, that is a absolute value. The ln of 3 minus 1 is equal to 1/8 of 1 squared plus c. Of course, this is the ln of 2. Notice the absolute value of 3 minus 1, which is the absolute value of 2, is 2. So we didn't have to do any funky business with that, taking the opposite of anything. That's going to be kind of clutch later on. Plus equals 1/8 plus c. So c is equal to the ln of 2 minus 1/8. Just leave it that way. And now we're in business, but we're not done, because we now can write the ln of the absolute value of y minus 1 is 1/8 of x squared plus the ln of 2 minus 1/8. So I've just taken this c value and replaced it with its equivalent. But that's, we have to get y equals. That was our goal, is to get y equals. And we don't have y equals yet. So if you remember, I'm going to put the training wheels on here for those of you who are not comfortable around logs. ln is log base e of y minus 1 equals 1/8 of x squared plus ln of 2 minus 1/8. Because we didn't have to do any funny business with our particular solution, we don't really need these absolute value bars, so we can kind of turn them into a parenthesis. We didn't have to take the opposite of 2 when we did 3 minus 1 here. That was 2. The absolute value of 2 is 2. So we're going to consider y minus 1 to be y minus 1, not the opposite of y minus 1. So now we can say the base, which is e, raised to the answer, which is this mess. Let's see, 1/8, well, let's call that 1/8 of x squared. Let's call it x squared over 8, plus the ln of 2 minus 1/8 equals what you're taking the log of. So the base raised to the answer equals what you're taking the log of. That's my little mantra. The base raised to the answer equals what you're taking the log of. So e to that answer equals y minus 1. So if you add 1 to both sides, you get e to the x squared over 8 plus ln 2 minus 1/8, and all of that stuff is our exponent, plus 1 equals y. There's a particular solution. It's a little bit ugly because of that nasty exponent that we have there. I think they would probably take that as an answer, but I want to show you something just so you recognize it. Remember, if you have like bases, x squared times x to the 4th, you can write that as x to the 2 plus 4. So if you saw x to the 2 plus 4, you could rewrite that as x to the 2 times x to the 4th. Well, that's what we're going to do. We have e to the x squared over 8 times e to the ln of 2 times e to the negative 1/8. Because we have addition of exponents, that means you're multiplying these like bases. So in other words, if I gave you this problem, simplify this, you'd recognize, hey, all I have to do is add these exponents. Well, the reason I'm doing this is because this one here in the middle, e to the ln of 2, you should recognize simplifies to 2. So that becomes a 2, and you're left with the e to the x squared over 8 times the e to the negative 1/8. Well, that's a little awkward to have those two separate e's there, but we can deal with that and add them together and basically get x squared over 8 minus 1 over 8, and then we realize, hey, that's a common denom, so e to the x squared minus 1 all over 8. So that is equal to this down here. So we can write our cleaned up version is y equals 2e to the x squared minus 1 all over 8 plus 1 from this plus 1 down here. So there's our final answer for the particular solution. If this freaks you out a little bit, you get to this and you need to go through this exponentiation, hang in there. This is common. Don't be surprised if you get a differential equation when you separate the variables. You're going to have a y's in the denom, which is going to give you ln's. So there are other ones available like this, and I can make them available to you. But let me know if you have issues with this. Shoot me an email, and I'll give you more examples.